Hi and welcome back to today's class. Um, this is week 5, right? And we're going to be this is going to be our last week of talking about mechanical, anything mechanical or HVAC. And today we'll be focusing on duct design, right? Duct design and air distribution, right? So today is not going to be very um tasking or demanding. So let's just get right into it, right? So first, talk about airflow calculation, friction loss, velocity limits. Well, to be fair, um, you already know we use CFM to measure our air volume of airflow, right? Volumetric airflow, right? And because it is the US we are dealing with, CFM is the unit that they use there. Liters per second is another way to measure volumetric airflow, but it's barely in use. It's just CFM, right? And there's a way to convert across, right? Then airflow basically starts from the cooling and heating load and then the temperature difference. That is why from when we are doing our manual N for commercial and manual G for residential, we discover that it's basically to just get that load, right? And also another reason why I need to specify the location is to get what the environment, um, the climate there is like, and that gives us the temperature. And then when I like do a difference between that and the design temperature, you're good to go. So those are like the two main reasons, right? Or two main factors that determine the air that's supposed to be accepted or supposed to be flowing into a place, right? So already talked about rule of thumb before, 400 CFM per ton, right? And that is just like an average value, like a base value. It could be more, it could be less, right? So it could go as high as 450 or maybe even higher in some cases if the 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 condition calls for it, right? So I'm sure that some ACs are designed to perform at higher values. Okay, moving on, talk about friction loss, right? Friction loss and pressure drop. If you remember, there's one time that there's this duct sizing. That when we did duct sizing on like one of our projects, we spoke about friction loss, right? And that is usually measured in what's this thing again? Water something. Let me confirm. Hmm. I usually just take that 0.1 value. I don't usually confirm what it is, but I don't have internet. Okay. So it means um water gauge per foot is a way of measuring the pressure a liquid is under, and definitely friction will probably be a function of it too, right? So a function, right? So yeah, friction loss has just basically the resistance air experiences as it flows through, and it just basically has to do with the surface. The surface is in contact with the roughness, the area, and all that. You remember friction from back in school, right? And these are like the design values we use 0.08 to 0.1. If you remember, even on our duct sizing software, we used to use that zero point 0.8, right? So that's 0.1. Where's that thing? Mm, okay. So usually, yeah. So this is where the head loss is, right? That's 0.1. Okay. So why it matters, why you need to like consider friction loss is that if the value is too high, it results in a noisy system because as the air is flowing against rubbing against the surfaces, it creates noise. And that is also another reason why ducted system is not really um liked more. That's one of the disadvantages of ducted systems, the fact that leads to noise. Then usually it also requires high fan energy because the the air is going to lose velocity very fast. So it needs like the fan to blow it even faster or higher, like more energy is being expended to like transport the air basically. Then if the value is too low, it results to oversized ducts, right? So like in the sense that when you put in that, just like when you're filling in that 0.1 in this software, if you increase the value, obviously the dock it will require a larger, let's say 2000 CFM. If you put it at 0.1, see 18 inches, if I increase it to 0.15, therefore, right? So if you reduce too low, I made a mistake. I was increasing the value, supposed to reduce the value. So we usually use 0.1, right? You see the size of the duct. If you reduce like 0.05, you see it increases the size of the duct, right? So basically, I also mentioned one time that square or um, ducts that have like a square, even cross-sectional area or even cross-section, like the width and length is like closer to each other. It usually helps for lower friction, right? But that won't always fit into spaces where maybe when you're putting the ducts through a floor, like if the floor divides two floors, basically not a ceiling. If it's in a ceiling on an attic space, you can size the duct as big as you want, right? You can try and get that square size as much as you want. And some cases you can even try to select circular ducts, right? But the thing now is that circular ducts, when you are attaching, um, one of the problem in circular ducts is that attaching like fittings to the sides is usually a bit tricky, because in that you are trying to get to lower any like possibility of leakage. So and then you know that you have to make holes and attach, and you know that for a circle, just like on the edge of a pipe, think of it like a pipe or a barrel. So first of all, to cut that flat space, and when you want to attach something on it, there's like a curve. So around the two edges, around the up and down, you will have to like go the extra mile to like seal it up, and it's still not going to be as airtight as it should be. That is one of the disadvantages of selecting. Even if that's one of the disadvantages of selecting circular ducts, but still, it is a good option. So okay, in that case now, square is usually just like perfect, right? Some people select circular ducts because they want to just like improve the aesthetics, especially in cases where maybe the ceiling is not they don't have a ceiling, the design doesn't like work with the ceiling, and then you have like exposed ducts just suspended in the roof area, like under the roof, and maybe like a commercial building, like a mall or basically a place where they have to interact with like maybe customers or clients, and they want to like improve even the aesthetics, even if they don't have to interact with such people, probably just want to improve the aesthetics. Circular doors are usually like finer to look at, right? So that is just specific occasions. So when in doubt, just pick what works. Remember, functionality is the most important before aesthetics, right? But if you can get both, even better. So moving on. So yeah, it usually when the value reduces, it usually leads to oversized ducts and high purchase, because I mean by the time you have to like you're sizing your ducts and you're seeing larger values than it should be, you spend more money buying those larger ducts, you spend more money installing those larger ducts because now they are heavier and you need bigger of everything, basically. So now duct size, the one we usually use, which is the most common, is that equal friction method. In this one, we design all ducts for the same friction loss per unit length, right? So no matter how where the like in our designs, if you notice wherever the value the extends to, we still use that same value of 0.1 and just change the amount of airflow, right? So you just choose the friction rate which you selected as this, and then you size the main duct for total airflow. So you've already gotten like the amount of air that you're going to flow through that space, and then just fill it in, right? Just like we did here. So this is the airflow, right? And then this is also velocity. We don't talk about velocity a lot, right? This is the velocity. Then you reduce the duct size as airflow reduces, right? This is just basically adjusting it accordingly. Then another thing we've not really talked about, we have actually, is balancing dampers. Basically dampers are like valves, right? So they help to control the flow of air, just like how valves control the flow of liquids through pipes, right? So in some cases, so why is it this is important in duct sizing is because if you have a branch, right, or you have a couple of branches, let me look for something I can use to explain that, right? Yes, this. So now these are branches off. Now you see that it's easier to attach because of this flat surface, easier to attach a flexible duct to this main duct. But imagine if this was a circular duct, it's going to be like curved around, and then there's a bit of challenge attaching this to that. So yeah, I was trying to talk about okay, balancing dampers, right? So balancing dampers, let's talk about dampers first. So for example, now air is leaving this equipment and it's supposed to flow out like this down to this part, right? So I mean, as it flows down here, it reduces in velocity, and it might even get to a stage where it becomes static, right? So it's as it's going, the farther it goes, the slower it gets. So now you might want this place may have like a higher demand of air than this place. For example, this might be supplying an office, another office no longer in use, or maybe the occupancy is low, and that means lesser air needed in that space. So the whole point of having a damper inside these ducts, right, is to slow down or to stop the air flowing in here, so that that air now is in a channel to another place. So that is like what the damper does, right? So it just some of them are like smartly controlled in the sense that they're automated, so that we know we talked about energy standards some time ago, so that as it's not flowing here, it's going to go here. So the system is just automated in that manner. So I mean, there are different type of dampers. So balancing in this case just helps to like ensure that there's like proper distribution of airflow from one point to another, right? So now another advantage, or rather the advantages of sizing is that it makes the work easier to design, because at least sizing is ahead of the design. It helps to, it's just like a pre-design type of um, step that helps you to like, if for any reason I need to increase the size of that system or reduce it, resize basically. When you size it up, it helps you to see if this is necessary or not, right? Then it works best for commercial building, because this is where like standards are so high, because there are some things that I can tolerate in your house, and then maybe sometimes the demand is not so high. But if it's a commercial building, you are dealing with the public, and you need to like ensure that there's no like bad experience or poor experience or poor review about your building, right? I mean, something as little as a badly conditioned church or a badly conditioned mall can reduce the people that come in there. So you need to like ensure that the place is as comfortable as possible. So the disadvantages now is that, I mean, this of this sorry, this method, actually this equal friction method, right? So these are the advantage of that method, is that it is good for design, easy to design rather, and then it works for a lot of commercial buildings, except in specific special cases. Then the disadvantage is that it usually requires balancing, because you've already your mind is that you're using the geometry of the ducting, and then the location of the other types of ducts to just achieve that balancing. So most times you need like assistance by adding balancing dampers. If you remember, we installed what they call it, volume control dampers in one of our projects. Let me see if I can find that project. So yeah, this is that winery project we worked on one time, right? So you notice now, especially in like the most basic system. See, it's not even here. Okay, it's not here because I use this number 4 to indicate it. Let's check what this is. Okay, volume control damper to be placed on all main supply ducts. So this just helps to balance out the this thing, basically the flow, the distribution, right? I mean, all this is just to improve the quality of the work at the end, and then it is a little less optimized than this. This is another method which we'll talk about shortly. So, but it is easier to do, right? And in some cases, you don't need to in fact, basically in some cases, that extra accuracy you're requiring might not really be worth the extra cost or the extra stress. Right, that is where this one works best. Another one type is called the velocity reduction method. Right, this one starts with a high velocity at the fan, and then as you're going, you're going to assume that the velocity is reducing, which it is actually. So this one is more accurate because before you're assuming that it's constant velocity, but this you're assuming that it is reduced as you go down. Right, this one is useful, very useful, and very good for long duct runs, because I mean the longer the duct, the more you see that effect of velocity loss, and then in larger air systems. So if you ever have to design a very large air system, very very large, this you would have to go and look for how to do this and then work with it. Then this one now is the most accurate, right? Static regain method. It is used for very large systems, and then it maintains near equal static pressure at terminals, right? And then it's more complex, rarely used in small medium projects. So I mean, obviously the higher accuracy you need, the more complex your design method becomes. But we'll not talk about those two. It's just that first one that we usually use that we'll talk about. So next, let's talk about fittings, losses, and balancing concepts, right? So now it's not just distance. Distance is one of the reasons why the air loses its velocity and its energy. But it's not just that. Fittings also contribute to that, right? Fittings are those, let's go back to that project, right? Fittings are those extra things that you add to this thing, the ducts, right? That help to like just improve the system, right? This like this. Then even when you're attaching the register or the diffuser to the end of the duct, you use fittings. So it just helps, and then you have to be sized properly so that it is, and then things like this. Although this is like a branch, so it just helps to improve, helps like with the workflow basically, right? So now losses don't just come from straight ducts. I mean, the straighter your duct, the lesser losses, because by the time it has to go around on junctions, right, you start losing some air. And some things that, some ways like common fittings cause pressure losses from the elbows. Let's look at that again. Elbows, now this is an elbow. So if the air is flowing straight, it loses less pressure. But the moment it turns into a direction and turns again, at that turning, some loss is taking place there. So now you can help by, instead of making it a sharp turn, you make it a smooth turn, right? That is why when you are designing, you always, even in Revit, when you are designing the main duct, there's always this curve, because this is like a main point of losses, right? So if you see sharp 90 degree is bad for your design. Then T's and takeoffs, you saw what a T was, basically where one meets, and like this now is a T. So it goes here and then it branches off. This is a T. But there are some cases where it will even go, maybe if it come and meet two splitting up like this, it's also a T. Right? So places like that basically lead to, and then transitions. What are transitions? Transitions are here. Transition is when it's changing from different cross section to another, either increasing or decreasing. Most times it decreases. Right, so this is 22 by 10. This is 22. Then this is 12 by 10. This is a mistake actually. So this change the cross sectional area. You see, also you have to make it smooth. If it was just attaching this here, maybe it just came here like this, there's going to be a lot of loss. But by making it smoother, it also helps. And then dampers, right? Dampers also result in a bit of loss too. So anything that just tampers with that natural flow causes losses. So some design practices, best practices that you can use is that you use long radius elbows, not sharp bends. I already showed you that what the long radius elbows looks like is that curve, this curve, right? Instead of sharp bends like this one. This is not advisable. Even though in this, why indeed this picture they're just trying to show us something else, but this, don't do this, don't ever do this, right? So avoid sudden changes. Instead, use transitions like this. So don't just attach this to this the way this is attached to this. Such places are areas of losses. Then keep branch takeoff smooth. Places like here where the branch is being taken off. keep it as smooth as possible. Try to avoid any form of unnecessary um, disruption. So now these are some other extra best practices in like locating your what do you call it, your flexible duct. So in this case now you see that it's leaving it off both sides, and this is okay because this is an area of loss. So while the air undergoes some changes here, so it's good that it does handles it all at once. It does it all at once. This is almost equivalent to having one large duct coming out in one side, right? So this is okay. But when they are too close to each other, this is like making a kind of zigzag. So the air comes here, flows here, comes here, flows here, and that's already slowing down the air, and it's not good for the energy, right? So this is not good. So if you had to space it out, if for any reason you don't align them like this, you're spacing it out, try and give a bit of distance. It's also not good when you are taking a branch close to a change in direction or a change in transition. Basically you should try to reduce like the complexity of the air travels paths. Just make it easy for the air to travel as easy as possible. So fewer branches is better, except you don't have a choice. Fewer branches is better, right? That's why instead of, sometimes you can even decide to just branch as you're branching off. Instead of branching off close by, you can branch off this branch. That usually has less effect because now you're talking about only the amount of air in that space. Something like this, right? Instead of, like, I could have easily branched off here again, but fewer branches. So instead of that, I just had to take it off here and just supply here with it instead. So this is a good, again, it all depends on your discretion. One designer differs from another designer. So the way I do my things might not be the way you do yours. But just as far as you obey these little basic um practices is okay, right? So now this is a case where it is too close to a transition. It is 12 inches. Try and avoid this, right? This two is also 12 inches apart. Basically what this drawing is saying is that at least 12 inches, so it should be greater than 12 inches before the air you introduce another complexity for the air, right, in quotes. So now just keep more space, right? So moving on, balancing concept. So now balancing concept is just trying to like balance. Okay, so no duct system distributes air perfectly by geometry alone. So I talked about that before. So geometry is just the shape of the duct, how it is shaped and how it like turns, the direction, the sizes and all of that, right? And then where the branches are. So that's what the geometry is about. So now geometry is not enough, right? If you just use this kind of system, it's cool. But I mean, with increasing demand or increasing supply, increasing size of system, it is not as efficient as it should be. So that is where dampers come in, right? So you have volume control dampers, which I've spoken of before. You have balancing dampers. So you go and check the difference between two of them. But like I said, dampers act like valves and they help to control the flow, right? And then terminal boxes too. This all just help to introduce that extra efficiency into the air distribution, right? So next we have duct routing best practices, which we talked about before, but let's just do it on a more general note, right? So confirm your ceiling height, very important. If not, you have to redesign. Before you, like I talked about, like pre-design um, steps, things you do before you start your project and before you start designing. So you need to take your time to go through your um project. And I'm going to attach assignments or projects with like a lot of information. So it's for you to check the one that is necessary for your design and the one that is not, and then you would use what you need for your design, right? There are some cases where you may not get what you want or you need. You can make calculated guesses, do your research, and with time you get more experience that will help you to like give better um um decisions, better choices. But until then, try and adhere to some basic practices, right? Then next, identify structural beams. If there's a beams are usually like structural bodies, right? Elements rather. So you cannot pass a duct through a beam because it's going to compromise the integrity of that beam. So you need to check all these things. That is why in this industry or in this mechanical and plumbing design engineering, you would need to collaborate a lot with architects, with structural engineers, with civil engineers, because there's always an area of intersection across, right? So next, you reserve shafts early. So shafts are like I don't know if you've noticed, like on some buildings, on the exterior of buildings, you have like a part where pipes run, but it's sealed. So it's just like a separate part of that building that is set aside just for duct to pass travel from one floor to another. So you will not just want to see um, ducts just on the wall in a building, right? Or within an interior space. So there's usually a duct that's built around it. Sorry, a shaft for that duct to travel there, especially when it's going from floor to floor. That's when you don't have a choice. Most times, if it's a one-story building, you just have to design it. You place your equipment in the roof or in the ceiling or on the roof, and then you pass your duct down into the building and then enter the ceiling and it spreads out. That's the distribution where it takes place, right? But there are some cases where you may have need to go through a floor. Try and avoid it. If I'm designing for like multi-floor buildings, I usually like, especially if it's a a commercial building, because commercial buildings usually require ducted systems more because the demand is way higher, right? So I usually like to do one mechanical room per floor. That's like the ideal mechanical room per floor. And then in that mechanical room, now you place your equipment there, and then it goes up into the ceiling and then distributes its air, right? But there might be some cases, some limitations where you don't have that. So in cases like that, you just will need to pass it from, like, after you've specified the location of that equipment, you sent it to the floor that it is best for. Sometimes you might have to like send it extra of that air duct to another floor, either down or up. Most times down, down into another floor. And now by the time it's traveling down past the ceiling into the ceiling below, the duct will be visible. So this is a case where you need a duct shaft. There are some cases too, because of the location of the equipment, right? You may need to just travel to another location. So you design what this is, and then you ask for, like, you design and ask like the architect to implement it, right? Or the client, whoever you have to talk to, or you talk to somebody and try and reserve where you want your shafts to, your duct to pass through, right? So moving on, we have, okay, when you're routing, you select the shortest path, right? Shortest path, because that helps to conserve energy, and then that helps you deal with less energy loss. Then you select fewer fittings, fewer branches if you can, right? Try to avoid too much, right? Then also try, as you're designing, also consider that it's going to be maintained. Maintenance is going to take place, right? Don't design, when you're designing, as you're routing it, make sure that you're thinking ahead also, because you may be the one to also work on the maintenance too. So you don't make it difficult for the next person, right? So next, duct sizing in Revit, right? So in Revit, we've used Revit a couple of times, right? And basically for me, I usually prefer to stick to AutoCAD because it's simpler to use, but you can go the extra mile and learn how to do it in Revit, right? I'm not going to teach how to use Revit fully for design. It is a whole masterclass of its own, right? It's a whole masterclass. It is more test demanding to learn, but it is more rewarding over time, because it also helps in collaboration. It also helps in like more um, realistic designs, right? So right there in Revit, there is a way to size, right? So the Revit basically comes with it, because it's made. AutoCAD can do a lot of other things, but Revit is made for buildings. If you notice, there's like the option for duct size, right? So you define your system parameters. This is if you're when you're doing the Revit. I mean, most cases this applies in both, across both Revit and AutoCAD. It's just in the mind. Once you get the steps right, is the tool doesn't really matter. Okay, so step one, select the duct material. In Revit, you can go as far. Now I talked about this material roughness when it has to do with friction, right? Then the friction method, you select the method of sizing, and then the velocity limit. This is the case where you need to like specify the velocity, which is FPM, right? Then step two, you assign the airflows, you must have already calculated the heating cooling load by now, and you have gotten the amount of air you want to get into that space. So you already know the amount that's coming out from each terminal. So you just select it, fill it in, and then Revit is going to calculate the flows automatically, right? It's an automated system. Then step 3 is to use the size ducts. Right. So after you inputted your parameters, you've done this, done that, simply use your size, you size it, right? This is something that we usually do manually, right? And then manual refinement. Obviously, it is a computer that is doing it for you. So you as a human being, you use your discretion and you use your intelligence, your years of experience to determine if something is right or wrong, right? So there might be some cases where it's going to give you an oversized transition, but you're able to like use your eye and check, okay, no, this should not be here, this should be here. So after it has given you that size your duct, size your system for you, you make your corrections or make your refinements, basically, right? Okay, so let me just do a bit of Revit. So it's not be as if I'm just speaking and not doing right, because sometimes speaking is easier than doing in most cases. So let's just quickly do like another similar design for this. Let me delete this because I don't need it. Oh no, I don't need the whole thing. This is a project we've worked on in the past actually. Oh, interesting. Not okay. Okay, let me just delete. Or let's just leave it there. So I'm going to use as a template, right? So let's add an equipment, and then okay, this is a fan powered VAV unit, right? VAV. Let's just add this. Now I can use press spacebar to change the direction and then the orientation rather, and then mount it maybe here, for example, right? Normally this is as I'm assuming to be mounting it here, right? So when you click on it, you can see that it already give you the dimension of the out and in, right? So this is most likely return and supply, right? So this in, you see that there are two ins. I'm suspecting that one might be for maybe outdoor air, because most times ACs usually don't recirculate the only air in that space. They just like collect air from like another outdoor zone, right? Or outdoor ambient air basically. So I'm suspecting that's what that might be for. Right. So let's take, okay, let me turn this in around. Okay. So now my in is here, my out is here. I want to take it out. Okay, let's turn it again. Okay, I just leave it as this, right? So now click here. Okay, this is what I need. Okay, this is out. Where's out? Okay, this is out, just like what we have here. So I come here, over it, and then it shows me what I want. So it automatically attaches it to the duct. So I want to do something similar to what I have here. You see now, this is a bad type of junction, right? So let's correct that. So this is, you see what it is. Okay, this is a mitered rectangular elbow, but I just spoke about how they are not the best. So instead I'm going to select a round elbow, right? Perfect. So now similar to this, now each of you can see that it's already giving you like the separate what they are. You can see this one is a round, is a transition, because transition is basically used when you're connecting to ducts, right? What else? Okay, let's do a return. Let's see here. This is in, so it means, right? Okay, okay, see, this already even has the size of his own. I don't think I want to use that, right? Let's see what this one is going to give me. Create that. Right, this is the proper standard return. You notice it's similar size to this other one, and it's a different color too. So all these things. So I mean, there's a way to set this such that it automatically selects this thing for you. But I'm not doing that now. right? So you see, and if you notice, this is still a lesson on routing, right? If you remember, this part of the building is a refrigerated room, a cold room, right? And if it's I usually wouldn't pass a duct over it, right? Because I'm assuming that this duct is passing in the ceiling. I won't pass the duct over it because I'm not sure how high it extends, right? And it might, some temperature changes might affect. But if I had to, I'll have to like do like extra finding to see what exactly it is about, right? Okay, so that is it. So let's split this one. This is a duct. Let's select it. It's a duct. Split it. Where is that split? Okay, let's split it. This one I need. So where do you want to split? Okay, somewhere here. Okay, so now escape. I'll reduce this. Select the, I want it to be a smaller duct. This is the automatic distance. I want to maybe say 10 by 10. That's what this is now. This is a transition, and it automatically gives you a degree, a transition basically. So now let's add. Remember that air came out through here. Let's do replicate that for here. This is, so that will mean adding auto systems, adding a fitting, right? So now there are different, you can select the type of fitting you want. So you can select a T, you can select a transition, you scroll down. Okay, there's a lot of options. Let's go with, even this round elbow is actually a fitting too. So let's just work with this round transition. Is it what we want? Let's see. Okay, this looks like it. Okay, I want to place it here. I don't know why it's okay. Let's place it somewhere. I don't want to place it here. See, okay, that's all we want, right? So place it here, right? So now press escape. Now we can connect a flexible duct there, right? And come out here, and then you can attach a Bluetooth system, attach a terminal, air terminal. Okay, perfect. Now you can come here and select type of terminal you want. Terminal is a general name. It could be a diffuser or it could be, and then the sizes, you know, remember the sizing we talked about, right? So this one is 24 by 24. Let's see if we can change the size here. This is 12 by 4. No, okay, these are grills, right? And you see this is a rectangular grills. Let's see what it looks like. Rectangular because let's add it, you see. Okay, well, by the time you select it, it changes automatically. See, it has like different ways, right? Let's see what else we have. So this is a rectangular type of ducts. Sorry, type of grill, right? I mean, there's a lot of things. This exhaust, if you remember, there's exhaust, there's supply, and they have different parameters. Right? This return, this supply. So you mean you can look up how to import families or create families, because these are like already preloaded families in Revit, right? So if you want like a specific size or a specific dimension or a specific material, you come here and you do it, right? And let's see if you can even select materials for this. Okay, this edit type. Okay, you can make some changes to your this thing here, right? I mean, in the ones that are available, this is elevation, right? And this is the angle, right? So you see all this, but that is not like the point of our class. I just wanted to give you like an idea. Delete that. Delete it again. Okay, sorry. Delete that. Okay. What is this? This is a fitting. Okay, the transition from what you see here, right? So I mean, this is pretty much what it looks like, right? See, there isn't much difference between what this and what this is too. So I mean, you could practice on your own and see what you can achieve when you decide to do sizing or ducting for. And another good thing about this one is that you get to like be more specific and more detailed. If you select these ducts now, they will tell you the elevation. This 00 means it's on ground floor, and that shouldn't be the case. This is 9 feet. This is assuming it's in the ceiling, above the ceiling rather, right? So this, at least with Revit, you're able to like specify, make it more specific. But I mean, my scope in this class is extend to just AutoCAD, right? So I mean, you can do your Revit and see what you can learn from all that. So I think that's all. Let's just end the class. Okay, let's just go over the assignment I have in mind for you before I leave. Okay. So you have two. There are two. One residential building and one commercial building. This one is the residential building, and I promise you it's going to be an experience. So you have, let's look at an elevation plan. Okay, let's look at elevation one. Elevation is just the side profile of the building to show you like from north, south, left, east, west, right? While that is opening, what else can we look at? Okay, there's a door schedule. This will be helpful when you are doing your manual G. Then there is cover page, there's ground floor. What else should we look at? Let's look at the floors as a plan. Which one has opened? Okay, they are all still opening, right? And we also have staircase layouts. Just more details. I feel that this particular, exactly. Let's see what we have here. I assure you it's going to be a learning. This is like your final project for understanding mechanical drawing. Oh, this is the door schedule. So it gives you, okay, gives you the location. Okay. Gives you the location, leaves you the description, which is also part of, which also gives you an idea of the materials. Then gives you the tag, right? And then the dimensions too. Very helpful, right? So this is just like an idea of what it does you have on plan. But that is not open. Let me open them. Okay, perfect. Everywhere will not block for you. So this is second floor plan. So let's look at the elevation first. Okay. It's a very peculiar type of drawing. It is not a regular straight up building. It has roof extending from down to the up, right? Like basically along the sides of the project, right? Then this is like the south, the north. Notice they are different, and it's a very modern type of building. So I'll need you to explore all modern or any modern type of design you can explore, right? It's going to open your mind. And you see, this means that it is on a raised floor, so it's not a slab on grade type of floor, which is also what's annoying. This just means this is like support for the floor, so it's not directly on the floor. If you notice, see, ground level is this, sorry, ground level, then ground floor level, which is the first floor, is 2 feet above the ground floor. Then this is ceiling level, or this is the first floor. There are two floors basically, and then this is second floor. Second floor is almost like an attic, but when you look at the project, okay, let's see what the second floor looks like. Now this is it. So second floor has like a smaller area, right, just here, and then it consists of this place. I shouldn't be telling you this, but there's no need to hoard information, right? This just means that there's a void here. So whatever floor is below this second floor, this floor below it extends up here, right? That is the space. There's no ceiling in between, so just a void space that with a large or a high ceiling, right? So basically, this part of the first floor is sharing the ceiling with the second floor, right? You needed to see me using my hand to describe as if I'm looking at you in real life, right? Then this is like, this is not a wall. If you notice, it's not a wall, so it means the air is escaping through here, right? So when you are looking at this floor, you won't just, when you want to like size the, look at the floor size area, you will not just consider this as a closed space. You will like include it as if it involves here too, right? Okay, then this is a bedroom. There's just one bedroom. This is a residential building basically, right? So I mean, without too much, I mean, you have the dimension and all of that. So let's look at the other project, right? I mean, if you have any questions, I'm glad to take them. Okay, this one we have an architectural file, so prepared by the architects, and some of it contains okay. So like I said, part of this assignment is for you to discover, to go through a sea of information and check which one you need and all that. So this is, from what you see here, there's a life safety plan, right? Basically just have to do with like the parts of egress out of the building. So you can use it to check. There's a lot of information I can use in your design. This is like a call out, right? Okay, this one is a commercial building, is a cook, like a kind of restaurant. Good, you have our, I shouldn't be showing you this thing. It's supposed to make you for your work, right? Let me show you this thing. Okay, this is the floor plan. See how large this building is, right? You see the walls, you see the windows, see the doors, vestibule. This will be important. You will see something about this when you're designing, doing your manual N, right? Here's the bathroom. Okay, pretty much. So I'm wishing you all the best as you go on to do all the designs, right? Thank you for joining to this class, and wishing you the best.